Hey class, today we're going to be going over, let's see, what are we on? Lecture 15. We're going to talk about moles and mole ratios, stuff like that. Not the animal, the mole, something different. So let's go ahead and get started here. Okay, started off with a little quiz, see how we're doing. Okay, so hopefully you paused that video and tried this out on your own. So this is a combustion reaction is actually a type of redox reaction. And so here we're showing, see if I can get it here. So this reaction here is a combustion reaction. Combustion would be something combined with oxygen, gives you carbon dioxide and water, right? So that's a combustion reaction. Generally, these are just hydrocarbons. Okay. So which compound was reduced? So the easiest way for organic, right, reactions is to look at hydrogens and oxygens and not necessarily electrons, okay? So if we look at the carbon here, the carbon gained oxygens, right? It lost hydrogens and gained oxygens. So really, the easiest way to remember this is oxidation is gaining oxygens, okay? So that means that the CH4 was oxidized, which means the other one is going to be reduced. You could go into the definition though and say if you're gaining hydrogens, then it's being reduced as well. And the oxygen on itself is by itself on the left side, and on the right side contains hydrogens. So because it's gaining hydrogens, it was reduced. So O2 would be the reactant that was reduced. Okay, hopefully that's making sense for everybody. And this is just kind of a review of what we talked about. Again, I always just remember that oxidation is gaining oxygens. If you remember that, then you can remember reduction is gaining hydrogens, and then the opposite's true. Oxygen would be losing hydrogens, and reduction is losing oxygens. So, okay. So another thing to remember with oxidation and reduction, when you're looking at ionic compounds, what you need to be looking at is the electrons or the oxidation state. So when an element is by itself, the oxidation state is going to be neutral or 0. And when it's in an ionic compound, it's really just the charge that it takes on. So on the left side, iron and oxygen are both neutral. And then on the right side, iron gets a 3+ charge, and oxygen has a 2- charge in this ionic compound. So oxygen, in order to become more negative, had to gain electrons, right? If you remember the oil rig thing, oxidation is losing electrons, reduction is gaining electrons. So since the oxygen gained electrons, the oxygen is the compound that's reduced. The iron is the one that is oxidized because it lost electrons. Cool. Alrighty. Oh, and this is the other option you could remember, Leo, Gur. I think Leo the lion says Gur is what people say sometimes. Anyway, whatever works for you. Okay, so let's look at this example problem. Go ahead and try and pause it and do this by yourself if you want to. So this says write and balance the following chemical reaction. So ethane, and it gives you the formula, is burned. So that means oxygen's added. It's going to be a combustion reaction and produces carbon dioxide and water. Okay, so if you write the reaction out, ethane is burned. So you're going to add oxygen to ethane, and you're going to produce carbon dioxide and water. Again, this is a combustion reaction like we saw just a few slides ago. So that's writing out the equation. And then you need to balance the equation, right? So I'll walk this through here. So I like to draw a little table. Maybe this works for you, maybe it doesn't. But go ahead and figure out what works best for you. Okay. So on the left side and on the right side, I'm looking at, so this would be the divide between the left side and the right side. I'm looking at number of carbons, hydrogens, and oxygens on both sides. So on the left side, I have 2 carbons, 6 hydrogens, and 2 oxygens. And on the right side, I have 1 carbon, 2 hydrogens, and 3 oxygens, okay? So we need to get more carbons, right? So look at the lowest number here on the right side. We have 1 carbon, and on the left side, we have 2 carbons. So I'm going to put a 2 here for this carbon dioxide. And the left side didn't change. I always just change one thing at a time to keep it simple. We still have 2 hydrogens. Oh, sorry, 2 hydrogens. And then we have, what do we have now? We have 5 oxygens, right? Okay, so now we need to get some more hydrogens. Right, we have 2 carbons on both sides, but we have 6 hydrogens on the left side and only 2 on the right side. I'm going to save oxygen for last, because I don't know if you remember, but I told you that oxygen is, you want to save the pure elements for last, because when you put a coefficient in front of this, it only changes oxygen, which is really nice. Right now, I need to get 6 hydrogens on the right side, so I need to put a 3 in front of this water. But you can see that also messes with the oxygens. So just if you have any pure elements, oxygen or anything by itself, save those for last. Okay, so if I put a 3 over here, again, the left side doesn't change. I still have 2 carbons. I now have 6 hydrogens. Now I have 4 oxygens here, plus 3 is 7, right? 7 oxygens. So everything's balanced except for oxygen. So I need to change this 2 oxygens into a 7. And 2 doesn't go into 7 an even number of times. But if I multiplied 2 times 3.5, right, I would get 7. So now if I draw one last thing here, multiplying the oxygens by 3.5, I have 2, 6, 7, 2, 6, 7, and I'm balanced. The only issue here is that I can't have fractions or decimals for my coefficients, so I just need to double everything up. So I'd have 2 ethane molecules, oops, and 7 oxygen, and 4 carbon dioxide, and 6 waters. Okay, so that's how I would balance this. I'm going to back it up just so we can see how the PowerPoint will walk through it for us. Yep, put the 2 in front of the carbon dioxide, 3 in front of water, and then 7 over 2, or 3.5, and then multiply everything by 2. Okay. Hopefully you've got some good practice balancing those from the homework. So we've talked about balancing equations, and now we want to talk about what do these coefficients really mean, or, you know, we talked about how you balance equations because you want to conserve mass, right? So the number of carbons at the beginning should equal the number of carbons. You can't just create carbon in the middle of a reaction. Okay, so what these numbers really tell us is if you burn 2 molecules of ethane, okay, so we're burning 2, whatever, we're going to say molecules, 2 molecules of ethane, we're going to need 7 molecules of oxygen. So for every 2 that we burn, we need 7 oxygen molecules. And then the arrow tells us what we produce. So we produce, when this happens, we produce 4 molecules of carbon dioxide, and we produce 6 molecules of water. Okay, and that's what those coefficients are telling us. So we can use these as conversion factors, which is very helpful. We're trying to figure out, for example, if we wanted to create 100 grams of carbon dioxide, how many grams of ethane would we need? Those kinds of questions are what we're going to be using these numbers for. So another example would be, let's say you want to burn 300 molecules of ethane. Okay, so you have 300 molecules to burn. For every 2 molecules of ethane, we have 7 molecules of oxygen. So this right here is the conversion factor. Okay, so for every, and then we're using the coefficients in the equation to get these. For every 2 molecules of ethane, we need 7 molecules of oxygen. So what that tells us is if we want to burn 300 molecules of ethane, we're going to need 1,050 molecules of oxygen. And then if we converted from ethane to carbon dioxide, it would tell us for every 300 molecules of ethane, if we convert it to carbon dioxide, we're going to actually produce 600 molecules of carbon dioxide. And then for every 300 molecules of ethane, we converted that to water, we would produce 900 molecules of water. So you can see how these numbers allow you to make conversion factors, which can give you valuable information. Okay. So in real life, you don't measure things by molecules, right? You're not gonna say, hey, I got a container with 4,000 molecules of gasoline in it, right? You're gonna use weight or volume. So let's say you weighed a container of ethane and you found that you had 10 grams of ethane. How many grams of oxygen are you going to need? How many grams of carbon dioxide or water are produced, right? This is a lot more useful than molecules. If I told you I had 1,000 molecules of water, it's hard to imagine how much that is, right? But if I told you I have a milliliter or a gram of water, it might be easier to envision in your head. So in order to get from grams of ethane into molecules of ethane, let me back up. We need to convert grams to molecules. The reason we need to do that is these numbers right here represent ratios. So you can't use these conversion factors when you're converting between mass of ethane to a mass of oxygen or something. You need to first convert the grams of ethane into molecules, and then you can convert between molecules of ethane to molecules of oxygen using these numbers. Okay, so these numbers they only work if you're converting between molecules or moles, which we'll talk about. Okay. All right. So to solve these problems, we need better conversion factors, and we're going to be talking about the mole and molar mass. Okay. And then using these two numbers, we can convert from grams to moles using those mole ratios. And for moles, we could convert to molecules if we wanted. So we're just gonna talk real quick about what a mole is before we move on here, okay? Okay, so to understand what a mole is, basically, it's just a convenient amount of something. For example, 24 cans you would call a case of soda, right? 144 pencils is a gross. That one's kind of weird. I didn't know that. A ream of paper is actually 500 sheets of paper, right? A dozen is 12. So if I say I have 1 dozen eggs, that means I have 12 eggs, right? And so in chemistry, that number is called Avogadro's number. And all it is this huge number, 6.022 times 10 to the 23rd, okay? So what it means is 1 mole of something is Avogadro's number of that thing. For example, 1 dozen of something is 12 of those things, right? Well, 1 mole is going to be 6.022 times 10 to the 23rd number of whatever thing you're talking about. In our case, we usually use mole to represent the number of molecules in something. Okay, so 1 mole equals this, just like 1 dozen equals 12, okay? Hopefully that's clear. It's just a convenient amount of something. That's all it is. Okay, a mole is simply a number, okay? So to kind of just reiterate this point, because I want to grill this into your head, 1 mole of carbon is 6.02 times 10 to the 23 carbon atoms. All right, 1 mole of silver would be 6.02 times 10 to the 23rd, right? Again, it's just 1 mole of carbon dioxide is 6.02 times 10 to the 23rd carbon dioxide molecules, okay? Oh, I think I said silver. I think I meant gold here. Sorry, AU is gold. It's Latin for aurum. Okay, anyway, not that important. But 1 mole of water is this many water molecules, right? Okay, I think I've hit that enough times. All right, so let's look at this example. Glucose, which is a sugar, has this chemical formula, C6H12O6. So if we say that 1 molecule of glucose contains 6 atoms of carbon, right? Because this right here by itself is just 1 molecule. So within that molecule, you have 6 carbon atoms, you have 12 hydrogen atoms, and 6 oxygen atoms, okay? So that's what we have here. We could also say 1 mole of glucose would contain 6 moles of carbon, or 12 moles of hydrogen, 6 moles of oxygen, right, in the same way. So if we made this 1 mole, right, it's kind of like, the way I like to think of it is like, let's say you had 1 cheeseburger. 1 cheeseburger actually contains 2 buns, right? So if you have 10 cheeseburgers, you actually have 20 buns. It's the same thing. Even if you just have 1 mole of glucose, you actually have 6 moles of carbon. You have more moles of carbon because each mole of glucose contains 6 moles of carbon. I just repeated myself. But anyway, hopefully that makes sense. All right, go ahead and try this quiz here on your own. Give it a pause the video and try it out. Okay. How many moles of oxygen are in 0.15 moles of aspirin? Okay. So we can say that, sorry, before I do that. From what we learned before, if this is 1 molecule of aspirin, okay, that's the formula. So for every 1 molecule, or we could say every 1 mole of aspirin, we have 4 moles of oxygen, right? Because there's 4 oxygens in each. If you looked at this in terms of molecules, right? For every 1 molecule of aspirin, you'd have 4 atoms of oxygen. Well, instead of 1 molecule, if you had a whole mole of aspirin, then multiply that by 4, you get 4 moles of oxygen. And the question is asking for how many moles of oxygen, and we're given moles of aspirin. Okay, so if we start with 0.15 moles of aspirin, we can then use this conversion factor that we created, right? Just flip it around to say for every 1 mole of aspirin, we get 4 moles of oxygen, okay? And moles of aspirin cancel out, and your answer is in moles of oxygen, okay? Hopefully that's making sense so far. Okay, now if we switch the question a little bit, it says, how many atoms of oxygen are in 0.15 moles of aspirin, okay? So, let's see. Okay, so if we start out similarly as like we did before, right? This is the same thing. We figured out we have 0.600 moles of oxygen. Well, if you remember Avogadro's number tells us that for every 1 mole of something, mole shortened is just MOL, okay? We have 6.02 times 10 to the 23rd, right? Molecules. Or if we're talking about a single element like oxygen, that would be atoms, okay? Okay. So now we can take 0.60 moles of oxygen, use Avogadro's number to say for every 1 mole of oxygen, we have 6.02 times 10 to the 23rd atoms of oxygen, okay? Which gives us, if you do that calculation, your number of atoms of oxygen in 0.6 moles of oxygen, okay? Hopefully that's working out there. Yeah, I'll show you that in a second. Okay. So Avogadro's number, why is it this random 6.022 times 10 to the 23rd? And really just convenience, right? So 1 gram is equal to 6.022 times 10 to the 23rd atomic mass units. Okay, so an atomic mass unit is a set number of, like it's a fixed mass, right, of something, just a very small. And so basically it takes 6.022 times 10 to the 23rd of those units to get to 1 gram. And that's why the number was there. Don't worry, I mean, don't really have to worry about why that's the number. Just if you're curious, you just need to know what the number is. Okay, so now we're going to be talking about molar mass. So we've looked on the periodic table, right? And we've seen these masses, and we've talked about how they're weighted averages of the different isotopes and stuff like that. But really what's important is you look at the periodic table and you're going to see that silver, for example, weighs 107.9 atomic mass units, right? And this is basically a sum of all the protons and neutrons in silver, and that's how we've looked at it so far. But because there is 6.022 times 10 to the 23rd atomic mass units in 1 gram, if you run the conversion, you would see that 1 mole of silver, so 6.022 times 10 to the 23rd molecule or atoms of silver, is actually equal to 107.9 grams. Okay, so if you took that many atoms of silver and put it on a scale, you would get 107.9 grams of silver. Okay, so we call this the molar mass. So we say that the molar mass of silver is 107.9 grams per 1 mole. Okay, again, this is an equality, okay? And so we can write it as a fraction when we're doing calculations, just like we've seen before. And so for carbon, for example, is 12.01 grams per 1 mole, okay? And you'll see this with, I mean, you could look at the periodic table and you'll find these molar masses of all these different elements. Okay, so the number that you see below, the units are going to be in grams per mole. Okay, that's the easiest way to think about it. All right. And then the molar mass of a we just talked about elements. You can pull those right off the periodic table to find the molar mass of a single element. But if you need the molar mass of a compound, it's just going to be the sum of the molar masses of the elements. So for example, the molar mass of calcium pulled right off the periodic table is 40.08. The molar mass of chlorine pulled off the periodic table is 35.45. So since in calcium chloride you have 1 calcium, right? And then you have 2 times the mass of chloride. And that would give you 110.98 is the molar mass of calcium chloride, okay? Cool. So basically you're saying 1 mole of calcium chloride weighs 110.98 grams, right? All right. Don't worry about that part. Okay. Let's see. Molar mass is a conversion factor, right? I just talked about that. So if we can say 1 mole of methane equals 16.0 grams of methane, then you can put that as a conversion factor, right? 16 grams of methane for every 1 mole, or 1 mole of methane weighs 16 grams. And so you can write those flipped around like we've seen before with other conversion factors. So you may have a question that says, what is the mass of 12.5 moles of methane, right? So we're going to start with 12.5 moles of methane because that's what we're given. And we need the mass, so we need to convert from moles to grams. And we know that the molar mass has units of grams and moles in it, right? So that's what we're going to use. Moles goes on bottom so that it can cancel out here. And 16 grams per 1 mole is the molar mass of methane. So we can cancel out the moles, and we're left with grams of methane after we do that calculation. Similarly, we could start with mass. So like, let's say we have 50 grams of methane. Well, if you just flip the conversion factor you did before, the grams are going to cancel out, and you're left with moles of methane. So you can go from moles to grams like that. Also, you can go to molecules. Okay, how many molecules are in 50 grams of methane? So let's see. Oh, we started with. Oh, it's just using this first one here. So we know that 50 grams of methane is 3.13 moles of methane. So we can put that down here. And then to go from moles to molecules, we use Avogadro's number to get us here. Okay. Basically, I think the easiest way to look at this is, okay, so we can go from molecules, okay, over to moles. And we can go from moles to grams, okay? We can't really go from molecules to grams directly. So from molecules to moles, that's going to be Avogadro's number, okay? N sub A is kind of the symbol you'll see for it. And then from moles to grams, this is going to be your molar mass, okay? And this works in both directions. You can go from moles to grams or from grams to moles using the molar mass, and moles to molecules or molecules to moles using Avogadro's number. Okay. All right, go ahead and pause this one real quick. Try and work it out. Okay, so for this one, we need the molar mass of the aluminum hydroxide here. And again, this is just the sum of the molar masses of each individual element. Okay, so we have the molar mass of aluminum, which is 27.0. The molar mass of oxygen is 16.0, and the molar mass of hydrogen would be 1.0, right? These are rounded numbers from what you'd see on the periodic table. But we have 3 OHs, right? Each OH or hydroxide is going to weigh 17.0 basically, right? When you add these up. So just the sum of all those gives you 78 grams per mole. Okay, go ahead and try this one as well, this quiz question. All right, so coming back, we have the artificial sweetener aspartame. You know, you probably see this in you know, like diet sodas. That's where you'll see it a lot. How many? And the question's asking how many atoms of oxygen are in 225 grams of aspartame. All right, let's try and work this one out. So if you remember my little diagram here, we have molecules. We can convert molecules over to moles, and we can go from moles to grams, okay? Actually, let's see, how many molecules? Okay. We're going to do a more expanded diagram here. And these are pretty useful, I think, to write down. Hopefully it'll help you see where we're going. So you can go from moles to grams, okay? Sorry, starting over the last time. Here we go. I don't have a lot of space for this. Okay, I'm going to say moles of A. All right, over to grams of A. Okay, and you can go from moles of A to molecules of A. Okay, from moles of A, we can go over to moles of B. This should make sense in a second. Sorry, I just want to draw this out because I think it's a helpful diagram. Moles of B you can convert into grams of B. Okay, so I would write this down and have this diagram. It can be helpful. Okay, molecules of B. Okay, All right. So we're going to call A aspartame, okay? We're going to call B just oxygen. Okay. So we're starting with 225 grams of aspartame, which means we're starting right here, grams of A, right? A is aspartame. So we can't convert directly from grams of aspartame over to molecules of B, right? This is molecules or atoms if it's a single element. So it's atoms of B. Because we're starting with grams of aspartame, which is here, and we need to go to atoms of oxygen. We need to go all the way up here, okay? We can't go directly there. There is no arrow in the diagram that takes us there, okay? But we can go from grams of A to moles of A, and then we can go over to moles of B, which then allows us to go to molecules of B. So that's why this diagram is helpful. Looking at the diagram, you kind of map out the direction you need to go to solve the question. Okay, so to get from grams of A to moles of A, this is the the molar mass, okay? Is what we're gonna use. Just use NM there. So we'll start with grams of A, so 225 grams of, I'm just gonna put A, okay? Now to get from grams to moles, we need the molar mass of aspartame. This can be a doozy to calculate on our own. Let me see if it gives it to us. There we go. Okay, so we have 14 carbon atoms, 18 hydrogens, 2 nitrogens, and 5 oxygens. Add those all up, you get 294 grams per mole. Okay, 294 grams of A for every 1 mole of A. Keep your units really clear during these problems. This is where it can get complicated if you're not labeling things well. Okay, so we use the molar mass to get to moles of A. We're at moles of A now. Now we need to go from moles of A over to moles of B, and this is going to be our mole ratio that we're going to use. We talked about this a little earlier. Every 1 mole of aspartame is going to contain 5 moles of oxygen. So using our units, we're going to say 1 mole of A gives us 5 moles of oxygen, which is B in our case, right? Okay, so then we got to go from moles of B up to molecules of B. And so from moles to molecules is Avogadro's number. Right, so that's true here as well, right? And then molecular or molar mass would give us from moles to grams. But we only need to go grams to moles of A, then moles of A to moles of B, which we've done so far, and then up to molecules. So using Avogadro's number, we can say 1 mole of B gives us 6.022 times 10 to the 23rd molecules, or since it's just a single element, we're going to say atoms of B, right? Now we've set up the problem. So grams of A are going to cancel out, moles of A are going to cancel out, moles of B cancel out, and we're left with atoms of B, which is atoms of oxygen, right? Because oxygen is the B over here. And that's what the question's asking for. Okay. So, sorry, this is very, not a very pretty drawing. Not a lot of space up here. But I think this is a good chart to know, right? I'd practice writing this out. This could be very helpful. So see how the slide does it here. Okay, the slide takes you from grams of aspartame to moles of aspartame and then to moles of oxygen. And then in a separate step takes you from moles to atoms. That's another way to do it. But you can do it on all one line if you want, like I showed you there. Okay. Alrighty. That's the lecture on moles. These are going to be really important going forward. So if you you're probably seeing that everything just builds, right, in this class. There isn't a lot that we learn and then just forget. Radioactivity kind of is something that is just kind of thrown in there. But a lot of the other stuff really just builds on each other. Hopefully you're staying on track and getting this stuff down. If not, come to office hours. If my office hours don't work, send me an email and we can set up another time if you really need another time to come visit with me and work out some questions. I want to make sure you're not falling behind. So, alrighty, we'll see you in the next one.